Really the idea of superposition right now that we're looking at, constructive and destructive interference. So wave 1 is drawn like this, and then the second part of wave 1 looks like this. Wave 2 is similar on the other side. And then the next part was just a repeat of that first one. So here are the two waves, one in red and one in blue. They were shown on different graphs in the example, and the question said, these are the two waves that coincide, what is the resultant of the two waves? So when we look at this, we want to think of it this way. Think of them on one graph, and what would they sum up to? So if I think about these two pieces, they had the same amplitude, just so you know. Okay, they both went up to either 1 or down to -1 in this case. So when I sum together a height of 1, which is here, and a height of -1, which is here, the resultant in the beginning is going to be just 0 the entire way up until we get to here. Again, because 0 plus 0 is 0, but here it's 1 plus -1, that's still going to be 0. So the entire way, these waves are canceling each other. So this is destructive interference right here. Good question to ask because we're going to go over this here anyway. So this is an example of destructive interference, where you have a positive amplitude and a negative amplitude canceling one another out. Then we get to this point right here. The red line in the second case is all the way up at an amplitude of 2. Yeah, of 2. So let's extend that axis. And this is up at a height of 2 right here. So when I get to the part where we have a -1 and a +2, I sum them together again. And since +2 plus -1 is just 1, it means that the green wave is going to be here now in this part. And then finally, when there's no blue wave, this is going to shoot up to here with a height of 2 and back down. So again, let's take a look at what we have here. This height is 2 plus this -1. 2 plus -1 is simply 1, which is why the height is 1 right here. Then we get to this part right here, where the height of the red wave is 2, plus the blue wave, which is 0, and 2 plus 0 is 2, which is why the green wave is now up here at 2, and then it drops back down because the sum of 0 plus 0 is 0 over here. So this again is destructive, destructive, and nothing. 0 plus 2 is 2. This has no examples of constructive interference in it.
So how would you ask a question like that?
The same way it was asked to start. Find the resultant of the two waves. You can graph it, or maybe I'll give you choices. You have to tell me which one it is. You give me examples, and I could say something like this. Or identify what point there is constructive and destructive interference. So this example, this would be the exact, right, from here to here is destructive. From here to here is destructive because they're combating each other in those cases. But from here on, it's neither, neither, neither. Okay? When they're both on the same side as amplitudes. So if the blue and the red wave both have positive amplitudes, see how this blue wave has a negative amplitude, but the red has a positive. If the blue were, say, at a half, then it would be a half plus 1 gives you 1.5, and the green would be up here. And that would be a positive, and a positive makes it more positive. That's constructive interference. Okay, or they're both negative. If they're both negative, this -1, and make this red one here, maybe the red one was down here, -1 and a -1/2 gives you -1.5. It becomes more negative by adding two negative numbers together. So if the amplitudes are on the same side, pretty much it's going to be constructive. If they're on opposite sides, it's going to be destructive. Okay? Yeah, this would be either multiple choice or explaining. This is not really any math involved. It's just simple arithmetic, adding numbers. You know? So it would not be a math problem at the end, but it would be either multiple choice, where I ask you a question about what's going on, or short answer, where you have to give me some sort of a result and possibly identify locations of interference. Okay.
You mentioned about constructive and destructive part, but if one is on 0 and one is positive, would that be neither?
It's neither still. So it's just pretty much a repeat of the wave. So you're talking about this part right here.
Right.
Yeah. When the blue wave was 0 and the red wave was up at 2, the sum of 0 and 2 is still 2. So it's still on that green line where it's in the same spot as the red. So that's not technically constructive. The idea is that you need to amplify something to be constructive interference. Yeah? Good question, Lamont. Very good question. Something that we were going to go over anyway, so it's good that you pointed out. Anything else that was pressing, like a pressing matter when you were looking at the problem set that you wanted me to go over first to make sure we get to it? Yeah? Okay. That's good. That works. So let's get into some vocab to start this. So let's start with some vocab for today. So I'm going to talk about words. I might write some stuff down. I might not. But if anything I say is not almost second nature to you by now, you should probably jot it down at some point. So the first thing we talked about was the concept of simple harmonic motion. Simple harmonic motion. And the idea with this is that an object oscillates freely. An object oscillates freely from one max displacement to the other. So simple harmonic motion specifically did not involve friction. So we're talking about a pendulum that's released and it goes on forever. We're talking about a mass spring system that when you pull down on the mass and you let go, it oscillates up and down forever. Now, is this really going to happen? No. Okay, we're going to have some frictional losses either due to some air resistance, some resistance in the actual mechanism itself. So eventually it's going to come to rest. But with simple harmonic motion, we're assuming that it is following the same period every time, when in reality the period is actually decreasing every time. Right? Real motion, the period of a pendulum decreases until eventually it stops. Okay? So again, it might take a second. You did this in your lab the other day. It took about 1.2 seconds, right? 1.2 seconds for it to go from 30 degrees through equilibrium to the other side and back. And that's one cycle. Again, through equilibrium to the other side and back is one cycle. That's one cycle. When it's at equilibrium, we know that it's going as fast as it can, right? That's the fastest point at equilibrium itself. It'd be like down here somewhere. And when it's at equilibrium, it goes as fast as possible. When it's at its max height, it stops. The same thing with a mass spring system. Think about a mass spring system. When the mass is going back and forth and back and forth, when it gets to the extremes, when it gets to its max displacements, a mass on a spring stops, and then it gets pulled back, and then it stops, and then it gets pushed forward, and then it stops, and then it gets pulled back, and the spring continues to push and pull over and over again, just like gravity pushes and pulls on this. And gravity doesn't push really, but just like gravity affects the motion of a pendulum. And we talked about that, gravity being the restoring force for a pendulum, whereas the spring force is a restoring force for the mass spring system. Okay, those are the restoring force ideas. Anyhow, back to simple harmonic motion. If we do account for any sort of dampening, okay, if we look at damped harmonic motion instead of simple harmonic motion, what would that be like? How would I draw a graph of that? Because, right, simple harmonic motion assumes, by the way, the reason we did this graph is because this is what it is. Simple harmonic motion just occurs forever and ever and ever. And it's continuously going to occur. Assume my wavelengths are all about the same. I know they're not. It's not easy to draw a perfect cycle. So assume that they're about the same length. What would an example of something look like if the motion were damped? If it were damped harmonic motion. So I'll give you an example physically, and you tell me what the graph would look like. So the pendulum, you raise it up to here, and it literally does this, and it eventually just stops in the middle. This one, right, that you're seeing in front of you is literally this. Over and over and over, never stopping. Max amplitude, max amplitude, max amplitude, max amplitude. And that's where we get to the top, then the bottom, and the top, then the bottom. Every time it passes equilibrium, that's crossing the x-axis. Then it gets to the maximum negative amplitude. Then back to the x-axis at equilibrium. Then back to the positive amplitude. So what's going to happen if eventually this wave dies down?
The amplitude of each of those waves is going to be smaller.
Yeah, successively smaller. Very good. That's right. So each time what's going to happen is this graph, instead of starting and continuing, it'll get smaller, and this amplitude will get smaller and smaller and smaller and smaller and smaller and smaller until you get to that. So the red graph there is an example of damped harmonic motion. We've used that phrase a couple times now. It was actually one of the sliders, if you recall, in that simulation on the FETLAB. The damping slider was one of them. So there are several types of damped harmonic motion. And you don't need to know these phrases, but just so you're aware of the idea. If the system quickly recalibrates itself, or if it oscillates for a while, there are two different types. So if you've hit a speed bump in your car before, for those who do drive and for those who obviously have been in the car with their parents or other people, when you hit a speed bump, the car will literally oscillate and then it will teeter out and it'll go flat. And that's what you're seeing right here. If it hits the speed bump and settles out too quick, like you feel the oscillation and the car jerks you back into place almost, like stops, you feel that force on your body. That's called an over-damped system. If it takes forever for the oscillations to stop occurring, and you go a couple blocks and then finally the car stops teetering off, you call that an under-damped system. But the idea I want you to recognize is that a damped system follows some sort of decreasing amplitude. It can be modeled by exponential decay, actually. So just to give you a little math background here. Oops. Okay, it can be modeled. See that blue line I just drew? That's an exponential decay curve. You guys do logarithms in math? Logs, right? Remember exponential growth and decay? That blue line there is like e to the negative x, exponential decay. These graphs that are damped harmonic motion do follow either exponential decay or some sort of linear or parabolic decay. So what you'll see that the curvature of the peaks follows that exponential, or it can be linear, where the curves are literally getting smaller and smaller in a linear fashion. And you'll see that. But the concept of damped is the opposite of simple harmonic, where it goes on forever. Yeah?
What is it again? The blue line?
The blue line is just it's like a exponential decay function. You don't need to, it's not going to be on the test, so don't worry. I'm just giving you background as to the data part. But the exponential decay is showing how it's going to progressively get lower and lower. The e to the x, don't worry about that. But the idea of damped motion you should understand. Vocab. Some of the words that we utilized. We talked about a lot of stuff. So we can start with amplitude, which we already discussed a couple times, but let's write down what we're going to do for amplitude. So amplitude is our maximum displacement, right? Our maximum displacement from equilibrium. So it's how far the oscillations go. If a guitar string oscillates up and down, and one time it oscillates up and down up to here, and the next time the guitar string oscillates further up, it has a higher amplitude. So on a graph, the amplitude is the height of the function. So if we look at this graph that's up here, just as we were saying a minute ago, here's the amplitude in yellow. But we notice that with damped motion, the amplitude keeps getting smaller and smaller and smaller until there's pretty much no amplitude, right? Look at the amplitude changing. It's reducing every time. So that's an example of amplitude where we see it getting smaller, yeah.
Will amplitude ever get bigger?
Sure, it absolutely could, yeah. Absolutely. I'm not saying that we're going to do an example specifically, but it absolutely can, yeah. So if I'm talking really low and then I talk louder and louder and louder, I'm raising the decibel level of my voice, which would be sound waves with a higher amplitude. Yeah. You can have uncontrolled vibrations, which occurs when you reach what's called natural frequency. Have you seen the Tacoma Narrows bridge failure? Has anyone ever seen that video? It's really cool. Cool. No, actually, nobody got it. Yes, actually, that's it. Thanks. I forgot it was up there. Yeah, have you seen the video of this? There's actually a lot of video of this. It's pretty amazing what happened. And what happened that day was exactly what you're talking about. It was amplitudes that were getting larger and larger. So the wind that day and all the other parameters occurring that day, temperature, wind, humidity, all that, it was like the perfect storm. It literally caused the bridge to find what's called its natural frequency. And then when that happens, the oscillations that were small at first became amplified. And they amplified to the point where they're uncontrolled. And they got so amplified that the bridge was oscillating so much that it just tore apart. It took a matter of like 5 minutes for it to actually happen. But that was oscillations where the amplitude was getting bigger and bigger and bigger every time. No. Yeah, so if you look at the bridge, you'll see it starts to sway. It literally starts to like do, you know with the slinky, when we did the transverse waves with the slinky and they were moving this way up and down? It does that in the video. I mean, you maybe not like this, yeah, you could pull it up right now. I don't want to waste a ton of time. Yeah, I mean, yeah, there you go. Just hold it up so far.
Okay, now you can. There you go. You just gotta go back.
Go back a little bit. Just to see the oscillations occurring. Like, it's not a joke, yes. It was crazy what was happening that day. And this was actually not long after the bridge was open. The Tacoma Narrows, but with a, I think with a C, right? Not a K?
C-O-M-A.
T-A-C. Tacoma Narrows. What state was this in? I don't remember the state. I do know, I think a dog died apparently.
I
Yeah,
think that was the only.
it was going to death, right? It was a dog, yeah.
42 mile per hour. Yeah, there are no casualties except for a dog trapped in a car.
Wrong.
How do you like avoid that?
Can you like avoid that? Like going over that bridge or dying over the bridge?
How do you?
So the bridge needs to be,
What did they
They-
do to bridges then?
yeah, so the bridge at that time was structurally sound, but they didn't anticipate the conditions of that day. And that's part of the idea of engineering. So I talk a lot about this in my senior engineering class, how you take precedent, just like with law cases, you look at all precedents to actually have in place, so like patent law and stuff. For bridges and for structures in general, you look at what's happened in the past. And as a result of that, they have to make sure that bridges were more structurally sound, that this condition couldn't be met, so they had some sort of forced harmonic dampers, they're called. If you've seen the new buildings that are being built now after 9/11, you'll see that a lot of new skyscrapers that have been put up are very, very new designs. They're made in a way such that the core of the building would still be stable even upon like an impact or a crash. If you've gone to the West Coast, you'll know there's a lot of earthquakes. And with earthquakes come vibrations. Those buildings have an actual core in them, God bless you, a core with a good amount of mass that is simply there to absorb the vibration. Nothing more than that. So you'll see there's new designs for buildings like that. And what you do is you put things in place to keep it from oscillating and vibrating. I have another cool video. If you remind me again, I can show you. It's only like 10 seconds, but I have to find it, so it'll take some time. And it'll actually show an example of that. So amplitude can be measured in meters, in degrees, in decibels. So if I think about a spring and I pull on it, then the amplitude is measured in meters. If I think about a pendulum, it's measured in degrees. That's the angle theta. So the units of amplitude are going to vary here. The second vocab word we want to get into, the second one was period. The period was the time it takes for a full cycle. The period was the time it takes for a full cycle. You might say the period of oscillation or the period of vibration. But the word period is what we're looking at. And that has a unit of seconds, and the symbol is tau. Okay, the symbol is tau. If you use the letter T, that's fine. I don't care. As long as there's something with time. Okay, but on your formula sheet, if you're looking for the formula, you're going to look for that symbol. Okay, it looks like torque. It's the same exact symbol as torque. Yeah.
Are there any formulas with A?
With amplitude, no. There are none with A, but A is just the general thing we use for amplitude, so I'll put it here. But yeah, there's no actual formulas with A involved in it. Now, what's interesting to note, and we talked about this already, is that the period and the frequency are inversely related. Okay, the frequency is using this symbol, omega. Okay, and frequency is the number of cycles that occur per second, or oscillations per second. Either way to say it, right? Cycles or oscillations per second. Per second. For frequency, yes. For frequency. So that's measured in hertz, and hertz are known as cycles per second.
Right, so for frequency, so 1 over frequency equals a period, and 1 over period equals a frequency.
Yep. They're inverses of one another, or reciprocals of one another. And let's actually take what Rain just said and lead that into our next point. Okay, so that's a formula we're going to jot down. So this is period equals 1 over frequency. And as Rain mentioned, we can switch period and frequency and just write frequency equals 1 over period. It's the same thing, really. So I'll write them both down. Now, there's a reason I'm doing this. Okay, I want to point something out to you. We've been talking lately about something called wavelength. In your lab, you noticed it was not the height of the wave. The height of the wave was the amplitude, but the actual width, the width of the wave, or length, I guess it's wavelength. The width of the wave, or the width of the function, was the actual wavelength. Now, if you go back to your formulas, though, I don't know if you picked up on this by now. Some of you might have noticed this, some might not. If you look at your formula, let me just scroll down a little bit so we can see this ball better. If we look at the formula, this is the formula V equals lambda omega that uses wavelength. This is a symbol called lambda that means wavelength. That is measured in meters. And this is still frequency, which is measured in hertz. Well, what I'm going to notice here, what I want to point out, is recognizing if you solve this equation for lambda, you get V over omega. Solve this equation for lambda, just divide by omega, you get V divided by omega to get lambda. So whether you realized it or not, period is inversely related to frequency. So is wavelength. Wavelength is inversely related to frequency as well. And you saw this in Lab 12, in that FET lab that you guys did, because what you had to do was increase the oscillation or decrease the oscillations, the number of rotaries that was turning, and it affected the wavelength. And they were inversely related. Inversely related, just like these are inversely related. Again, wavelength and frequency are also inversely related. Okay? Go on. Sorry.
What is wavelength?
Meters, any length. Meters, centimeters, kilometers, but the standard unit is always meters. And the base unit is meters. Okay, so if I look at a graph, just so we're aware of what I'm talking about right now. Okay, let me give you a quick example of what I'm saying. The wavelength is from either crest to crest, or trough to trough, or you can just think of the wavelength as a full cycle. That's a full cycle. So put a little marker maybe, right? This is where one cycle occurs. That's where the second cycle occurs. So one cycle is what I'm highlighting in red right here. That's one cycle. So that's really, physically, if I were to look at this, that's a wavelength right there. It's literally one cycle's length. If I measure from here to here, or from crest to crest, or from trough to trough, it's the same answer, assuming the wave is not changing in its frequency. Assuming that these vibrations or oscillations are not getting faster or slower. Okay?
It can also be 2 times the length from the crest of the trough.
You can do that as well, absolutely. There is symmetry that exists, absolutely. Just like the amplitude on the top is the same as the amplitude on the bottom, yeah. There's a lot of symmetry occurring here.
Because I think there was a textbook problem that gave you the length from the trough to the crest.
And you had to double it to use the wavelength. And there was another problem, if you recall, where a pendulum was swinging, right, from here, and it said something about going through equilibrium. Well, the first time it passes through equilibrium, when it starts here, and it hits equilibrium, that's only a quarter of a cycle. And that's a half cycle, and that's 3/4 of a cycle, and then back is a full cycle. Remember, this is half cycle, full cycle. So if I'm going to go to here, that's just a quarter of a cycle. Okay, so keep that in mind when it comes to this stuff. Very good. Now, what I want to point out is this. If I were to now call this graph something as a function of time, x as a function of time, then this distance from here to here, although we're calling it wavelength, is the time it takes for one cycle. And what's the time it takes for one cycle called, though? What did we call that? The time it takes for one cycle to occur. The period. So the wavelength and the period can actually be interchangeable at times. Okay, the wavelength and the period can be interchangeable. They sometimes can be the same thing if we're talking about something. If we're talking about something specifically here that is a function of time. And that's the reason that you have this indirect variation here and here. Both wavelength and period are indirectly related to the frequency. Indirectly related. The more frequency, the lower the period. The lower the period. The less the frequency, the higher the period. Higher frequency means more waves are occurring. So higher frequency would look like this, ready? You would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 waves occurring maybe here. That's a higher frequency wave than what you're seeing here. Okay, so higher frequency simply means it's like taking the wave and compressing it, like you would compress a spring. Same concept as that. All right, some formulas I want to get into. Any questions so far? Questions besides what you've been asking, which is good.
So the wavelength is smaller, the very high frequency.
Correct, because they're indirectly related. Very good.
And frequency is lower, longer wavelength.
Correct. Yep, absolutely. Okay, so you can think about the wavelength itself, just squeezing the wave down. So let's look at a couple formulas real quick. Let's start with the main two that we were referring to. So these two formulas here give us a period of oscillations when something is set in simple harmonic motion. If it's not in simple harmonic motion, if it's in damped motion, this is not true. Okay, damped motion, what's going to happen is, you know what, over time, those periods and wavelengths will vary, and the amplitude will vary. So this is an example of simple harmonic motion and the time period it takes for these oscillations to occur. Yes?
We'll use for dance.
You would use a little bit of calculus, actually. Something that we haven't studied yet now. So you're not going to worry about the time period for damp right now. If you take AP Physics next year, you do, actually, yeah. That's one of the topics they study. Use differential equations to solve. So L and M. L and M, let's talk about those. Right? Why am I saying L and M? Why am I referring to them? What's the analogous nature going on here? What's happening physically here? Yep.
Those are the only two variables that really change the period.
Because those are the two variables that change or affect the period. Okay, I agree. I mean, K also does, so if the spring constant is different, that will change it. And G changes it, but we'll assume we're on Earth for now. But why am I saying L and M? Let's relate those to each other. L is the length of the pendulum. It's a physical property, isn't it? And what is M? M is also the mass of the object, another physical property that you're going to measure. You can alter the mass. You can make it a heavier mass, you can make it a lower mass. You can make it a longer string, you can make it a shorter string. So as Steve said, things that you can alter or change, but those are both properties of the apparatus itself. Now, K is kind of also a property of the apparatus, but it's the spring, not the mass. So K is the strength of the spring. A stronger spring means it's going to pull back faster. So a stronger spring means a higher K value. If you increase this, it's going to cause this to decrease because these are indirectly related. These are tau and M directly related. If you have a heavier mass, it's going to oscillate for a longer time period. And you guys saw in the lab that the length was the one thing that mattered for the pendulum. Everything else that you varied for the pendulum barely had any effect. But the minute you had the length, you saw a big reduction in the time period. The length of the pendulum affects the time period. Why couldn't we vary this in the lab? It's not a hard question, I'm meaning honestly. Why couldn't we vary this?
Because gravity is always length.
Yeah, gravity on Earth at sea level, we're not able to suddenly get up to the top of a mountain, and even there it's very, very, very minimal change. But gravity on Earth in general is around 9.81. So G can't be very much, so we didn't see that effect in the lab. So gravity is lower on a higher elevation, so that would make this number less. Lowering this number would increase this number. It asked about the period of oscillations?
No, I think it asked just what would happen to gravity, if it would like stay the same.
The clock. It's like it's
Yeah, like it's
clock
speed
right
is.
now.
Okay. You have it? Thank you.
The clock, sea level versus 1.
Okay. So if you're at a higher level, right? If you're at a higher level, there's less gravity. Less gravity means it's going to take longer to swing, right? So how do you compensate and fix that? You shorten up the length of the actual knob. Think about it, right? If this is lower, it causes time to be too much. It's taking too long for this thing to swing, right? If I'm somewhere where there's very little gravity, what happens? It goes real slow. Really high gravity, like Jupiter, it's going to go back and forth really fast. So if I have really low gravity or lower gravity, like on the top of the mountain, it'll make the time period longer. So if you were a mechanic and you were trying to fix a grandfather clock on the top of the mountain and it was taking too long to swing, you should lower the length. And you guys saw that yesterday. When you lower the length, you lower the time period. Okay? Yeah.
Can you repeat that?
If you have too low of gravity, where gravity goes down, it's going to cause the time period to go up. And if you want to account for that, and it's taking too long to oscillate, just take the rod that's holding the grandfather clock and shorten it. Make this a little bit shorter so it lowers this number a little bit. It's not answering the question. I don't know what the question asks. I'm just giving you guys an idea of what you would do. I don't even know what the question asks. I didn't look at it. So if it's running slower, it means the time is running slower. If it's running faster, it means the time is running faster. If you had this number decrease, it causes this increase, which means time is taking too long. The time periods are too high, so we cut down the length a little bit to lower this value, actually. What else for this? Obviously, know how to solve for something under the radical. So let's show how to solve for L or G, okay? Just to make sure that we're all clear on this. So I would get rid of 2 pi right off the bat. I would square both sides right after that. So start by getting rid of 2 pi, square both sides. And now, depending upon what you're trying to find, you can take a different approach. I've noticed that some of you in your homeworks and parts that you've done this before, even on the lab when you were doing this, when you try to solve for G, some of you have been dividing by L. So you can divide by L because L is currently in the numerator, but if I divide by L, it leaves behind a 1 up here. So you're solving for 1 over G by dividing by L. So if you want to solve for G itself, I would just take G and switch it with this entire thing. Think of this as a number. This is a number. Take this whole thing and put this entire thing in the denominator and move it with G. That's how you would isolate G. It's the exact same thing to isolate K. It's the exact same thing on the right to isolate K. How would I isolate L? I would just get rid of G. How do you get rid of G? By multiplying G up to the other side. So again, if I'm trying to get L by itself, just take this guy and multiply it up on both sides, and G is gone. And there's L. So that's the expression for the length of a pendulum. You would need G tau squared over 4 pi squared. The same thing is true up here. If you want M goes in for L, K is where G was, and it's the same thing. M equals K tau squared over 4 pi squared. So it's going to be the same concept each way. But the harder one, I think, that most students struggled with was the idea of solving for the unknown denominator. So again, I would literally take this and just switch their positions. Okay. What's the common mistake here? I talked about in your calculator, make sure to put parentheses around the product in the denominator. So if you're going to do 4 pi squared in your calculator, and you're not going to do it ahead of time, and you're going to do all this in one step, that's totally fine, but make sure that that has a set of parentheses around itself before you do the calculation.
Is it just for 4 pi squared or for the tau?
So anything in the numerator, you don't really need parentheses around unless you have a sum. Since it's a product, it doesn't matter. If you want to be safe, put your numerator in parentheses, and then hit divide, and put the whole denominator in parentheses, and then hit enter. Yeah, that works.
You get the same answer if you just like put parentheses around the whole thing and then square it.
Like that?
Yeah.
Yep, that's fine. And all I'm doing, right, is just putting a square here, a square here, and a square here, and that's what gives me this line right here.
And the calculator will do that for you.
Yeah, you could put the parentheses around the whole thing, but you need parentheses around the 2 pi and a parentheses around the entire fraction, and then you need to square it. See what I'm saying? So just be careful. Make sure you have parentheses around this, and then since you're squaring this entire thing now, you need another set of parentheses around this, and that value is squared. Yeah? So I recorded in the other class, and I did a couple of extra different things from their class, from you guys, and yours I did some different stuff. So feel free to take a look at this. Lab is due on Wednesday, and please also do survey. I'm giving you homework credit for that. Please do the course survey. No, I think I made it due next Wednesday, just so you can do it over the weekend. So you don't have to rush. Hey, today's a good day to have extra help. The game's not till 6. If you're just hanging out and you've been struggling with this work and you want a place to do work and hang out and stay, I'll be here for at least half an hour, an hour. Okay? Have a good day if not, guys.
That's why I did it.
Because it's a product, yeah. Anytime it's a product, you have A over BC, A squared, B squared, C squared. Well, no, listen, if it's a plus sign though, this is not true. You can't do that. So then you have to leave it. So this is right here, right?
And then you can that you have to square. Thank you.
Yeah, come on, feel free. I'll be here, okay?
How long are you here?
At least a half an hour, an hour. I mean, it's only 2:30. We have a while. I'm gonna probably go to the game later anyway, so I'm not in a real major rush. Okay? Yep.
Thank you so much.
You're welcome, ma'am. Can you do me a favor, Steve? Just write Clemence's name on the top. Oh, she's right there. You need to put your name across. That's right. I just don't want to forget. I know your handwriting, but I don't know if that's this.
To supplement Narrows Bridge, when I was doing my Brooklyn Bridge paper, there was a ton on, because, I mean, Brooklyn stuff came after that. And he used
Have a nice weekend.
Brooklyn
You too, Ray. Thanks.
Bridge a lot of what not to screw up in Brooklyn Bridge.
Is that right?
Yeah, I learned a lot
I know
about
that.
Brooklyn Bridge just because that was like, they observed what happened there.
And they saw that and said, hey, this can't have that again, right? It's true. It happens all the time. I mean, any sort of catastrophic engineering failure has been studied like relentlessly, and it becomes like your research studies that you do in college then. Like, you know, and like doctors, they call them case studies. It's pretty much another case study so you can do better on that next time.
I was watching, I was doing work, but I caught, Dad was watching Impossible Builds.
Yeah.
And last night, you hear about this thing in Dubai? Or, oh, no.